a soil experiences a certain state of stress in the subsurface. That state of stress, which is going to have some vertical and some horizontal stresses applied to it, can be captured in the tau sigma space by a Mohr circle that represents the state of stress at the point in equilibrium. If this is sigma z and this is sigma x, this will be sigma z and sigma x, and we're going to say that these are effective, and this state of stress is probably a K0 state of stress, in this case of a level ground. Then we're going to apply a footing onto the soil, and this will add additional stress changes, both in Z and in X. In a triaxial test, typically we change one of them at a time. For example, we apply a delta sigma Z or a delta sigma X in axial compression or lateral compression. So in the simplest of all cases, we would increase only sigma Z, but it may happen that we also increase sigma X, and so this will be delta sigma X, and this is delta sigma Z. And we would do that until the soil encounters the failure envelope, and that means that the soil has reached failure. Notice that from a point of view of failure, we are interested in the combined state of stress. The initial plus the additional stresses are the ones that bring the element to failure. From a settlement point of view, the initial stresses are already there. So what we are concerned about is the strains induced by the change in stress. Therefore, when we look at the stress-strain relationship, we are actually talking about the stress changes, let's say in Z, that are causing the strains in Z, and this would be something of this shape. Or it could have a post-peak strain softening, as we have seen in other discussions. To summarize this first point, I would like to insist we analyze failure with the combined stress state. In other words, we must take into consideration the initial stresses and the stress induced by the load, combine them to see whether the point is approaching failure. From a settlement point of view, we look at the strains caused by the stress changes because the initial stresses are already there before we start. How can we represent this curve? There are different options. For example, if we are concerned only on failure conditions, we could actually take a rigid plastic model. This is delta sigma with respect to strain, and this would be rigid plastic. If we would like to capture the initial part as well, then we could take an elasto-plastic model. But in some cases, the details of the transition from the elastic regime to the plastic regime begin to gain relevance, and so we really would like to have the full shape of the stress-strain behavior. And therefore, we go back to this stress-strain relationship, and we're trying to find also simple models to capture it. So one particularly useful one that can be very convenient is the result of plotting this curve in another way. Let's say that we plot, and I'm going to do it in terms of the shear stress and the shear strain because this is the most normal way of seeing this formulation. But please recognize that delta sigma Z would be, if sigma X did not exist, would be the change in shear. And so from here we get the shear. And also if we make a Mohr circle of strains, we will get the shear strains. Now, if instead of plotting it in this form, we actually plot gamma, the shear strain over the shear stress. For this type of behavior, the data begins to follow pretty much a straight line. It's surprising for any material until peak, any soil. And so this is the type of relationship. And when we express this further, when we write this, let's say that this is the intercept is A, and the slope is B, then we can say that gamma over tau is equal to A plus B gamma. And we would like to know what A and B are. So let's think about it. If the strain is very, very small, then this term disappears, and at very small strains, tau over gamma, tau or delta sigma z over gamma becomes the slope here. So for clarity, what I'm plotting now is tau, and in this direction I'm plotting the shear strain, but evolves in other way. And so tau over gamma, when gamma is very small, is this value which we call Gmax. And so that means that when gamma is very small, 1 over A, as gamma goes to 0, 1 over A is equal to Gmax. Now let's see what happens. What is the meaning of B? So let's say that gamma is very large. When gamma is larger, this term becomes very important, so A disappears out of this equation, and then the gamma cancels out, and that means that 1 over B at gamma very large is tau max, which is this value here, tau max. And so 1 over B is equal to tau max, or the ultimate tau, which is the shear strength of the soil. Now we're all set. And what we can say is, we are going to flip this over, that tau is equal to gamma over A plus B gamma, gamma over A plus B gamma, which is equal to gamma over A is 1 over Gmax plus gamma over B is 1 over tau max. And this is called the hyperbolic model for soils. And several interesting developments follow from this. Please notice that we are emphasizing on stress-strain relationships. We are not looking at the volumetric strain. If we want to do that, then we fall into something like, for example, critical state soil mechanics. What I'm going to do next is to multiply numerator and denominator by Gmax. And so this is going to be equal to Gmax times gamma over, multiplying in the denominator, this becomes 1, plus gamma times Gmax over tau max. Now, Gmax over tau max is where the asymptote at the origin, which is Gmax, and tau max intersect. So tau max over Gmax is this value here of a strain, which we are going to call reference strain. And so this is going to be equal to Gmax times the shear strain divided 1 plus gamma over gamma reference. This is not a threshold strain. This is just the ratio between the ultimate shear strength and the maximum shear stiffness. But this begins to tell you how Gmax evolves as the strain level increases. Let's start with a cleaner drawing again, and let's think of what is tau over gamma at this point. This is the value of tau, this is the value of gamma, so tau over gamma is the slope, in other words, the secant modulus. So G secant is equal to tau over gamma, which, as you can realize, tau over gamma becomes equal to Gmax over 1 plus gamma over gamma reference. We can go further and normalize and say that the secant modulus with respect to Gmax decreases as 1 over 1 plus gamma over gamma reference. And this is the degradation of the stiffness, of the secant stiffness, with a strain level predicted by the hyperbolic model. I could also compute what is the slope at this point. In other words, we're going to call G tangent at that location as d tau d gamma. And this is going to be equal to, I go back to the upper equation, is going to be equal to Gmax, and is u over v, so this is going to be equal to, if I multiply the second term here by itself, and multiply numerator and denominator, then what I'm going to obtain is that is 1 plus gamma over gamma reference, and this becomes square. Now I can combine the two. This is going to cancel with that, and I'm going to get that the tangent stiffness is going to be equal to 1 over 1 plus gamma divided gamma reference squared, and this is times Gmax. I could also normalize G tangent by Gmax, G tangent by Gmax, to obtain 1 over 1 plus gamma over gamma reference squared. And this is the modulus degradation curve predicted by the hyperbolic formulation for the tangent modulus. Going back to this figure, you can see that the tangent modulus has decreased faster than the secant modulus at any given point along the path, and indeed this is the case. For example, when the strain level is equal to the reference strain, the secant modulus is 1 plus 1 equal 2, so it's 1/2 of Gmax. That is the secant modulus. However, the tangent modulus is 1 divided 2 squared, so it's 1/4. This, you can plot both of them, but in general, they look as follows: gamma reference, and this is G tangent or secant over Gmax, and the curves are like that, as you have come to see, and depending whether this was G tangent, then this would have intersected at 0.25. This is when gamma over gamma reference is 1, and this will be 0.1, this is 10, etc. I can divide both sides of this equation by tau max, and I obtain that tau divided tau max is equal to Gmax divided tau max times gamma over 1 plus gamma divided gamma reference. Now, Gmax over tau max, or the inverse, tau max divided Gmax, is gamma relative. So this is equal to gamma over gamma reference divided 1 plus gamma over gamma reference. And I can solve for the ratio between gamma and gamma reference. and express it in terms of tau over tau max. Therefore, I can rewrite the hyperbolic formulation not in terms of the relative strain level with respect to the reference strain level, but in terms of tau over tau max. Furthermore, I can generalize the hyperbolic model. Now it will be expressed in terms of tau over tau max, and you will see that this leads to the Ramberg-Osgood model. But now it comes at the expense of having two additional parameters, but allows you to better fit certain soil behaviors, particularly when they have a more brittle behavior. In other words, they are not so smooth, but they are sharper going up, and there is a sharper transition. And you obtain that with two additional parameters, and you will find the Ramberg-Osgood formulation at the end of this presentation. Let me show you one more very useful application of these hyperbolic models and the generalization through the Ramberg-Osgood model. If this is what we are going to call the backbone curve, if this is the actual shear stress, shear strain response, and we load the soil to a certain point and then we unload it, then it's going to describe the following behavior. And then we reload it again, and it will go like that. And this area here is an indication of how much energy is consumed in the deformation. Therefore, this is attenuation, damping in the soil behavior. The way to obtain this curve in simple ways is you take the backbone curve, and when you reverse it, you attach it to the end, and you double both the height and the width. And that's called the Mason rule. And it's very useful for many practical purposes. So using the Mason rule and either the hyperbolic or the Ramberg-Osgood model, you can compute the damping ratio and the attenuation during wave propagation, for example, for soil dynamics and earthquake engineering. The formulation will also appear at the end of this presentation. We have not yet connected deformations, shear deformations, and volumetric deformations, and that is the purpose of the following video. In conclusion, if you are not too concerned about all the details, models that capture the asymptote at the smallest strains and at largest strains failure are sufficient for a large number of engineering analyses. And then we can begin gradually adding more details. The hyperbolic model is a case in point, and it can show us two things: the degradation of the stiffness with the strain, as well as the energy consumption in causing these strain levels.